via the continuation monad transformer. So there's a general way of taking predicates over a type and lifting it up to be a predicate over T of that type in terms of the continuation monad transformer that I showed you before when I was talking about Haskell, the thing which goes into T of R to T of R. So this is the work of Katsumoto, and that's been used by lots of people. And in fact, you've seen this by orthogonality idea twice already in my earlier talks. So the logical relation for the imperative language that I gave you, if you remember, the semantics there was defined in terms of continuations. When I defined the logical relation for computation types, it was defined in terms of taking a relation on values, turning it into a relation on continuations, and then pulling that back into a relation on computations. And although I whizzed past it rather quickly, there was a closure operator in the relation I showed for the effect system for the language with dynamic allocation. This Q-per closure stands for quasi-per, which is one of the extra properties that relations get when you put them through this process. And that's also an instance of bi-orthogonality. So finally, on the side of the kind of foundational semantics of these sorts of things, Alex Simson, Jeff Egger, and Rasmus Mogelberg have been working for a few years on something they call the enriched effect calculus. So I had a slide before which showed that there was some connection between the computational metalanguage and linear logic, that we have an adjunction between, if we have an adjunction between a Cartesian closed category on one side and a symmetric monoidal closed category on the other, then this induces a monad on the CCC side and a co-monad on the symmetric monoidal closed side. And so you have a model of linear logic with bang on it, and you have a model of the computational metalanguage with a T on it. And translations into those two calculi that we know and love are related by the adjunction. But this only works in the case that the monad was commutative. And this enriched effect calculus, I mean, it's not generally described this way, but you can think of it as being like a term calculus which corresponds to the general case where the monad is non-commutative. So you have a two-level language where there are types for values and types for computations, and you think of the types for values living in the base and the types for computations living in the Eilenberg-Moore category associated with the monad. So here we are. There's the separation into value types and computation types. The computation types are underlined here, and so we have a type here, linear arrow B. So this is the thing that matches the collection of all monad homomorphisms in the algebra homomorphisms in the Eilenberg-Moore category from A into B, as well as the ordinary function space down at the base between value types. And they've done lots of nice things with this. They've extended it with polymorphism. They've got lots of very nice results about type isomorphisms and the kind of things you can encode in here, and about the relationship between call by name and call by value and so forth. It's a very promising line of work, I think. So, moving towards program verification, separation logic, I guess, is something that everybody's heard about. So I think this is probably the most influential thing in the last 10 years or so in programming languages. Originally due to John Reynolds and Peter O'Hearn. It kind of came out in some ways of work on linear logic and on functor category semantics of Algol-like languages, but kind of delivers some of those ideas in a dramatically more usable form. So the idea is to extend Hoare logic to allow reasoning about programs that manipulate pointer structures in the heap, so programs that actually build linked lists and so forth. And the key idea that makes it all work is this idea of separating conjunctions. So in Hoare logic, if you try and do Hoare logic for simple-minded, in a simple-minded way for programs with pointers in, then roughly speaking, aliasing is the default. And if you want to say things are separate, then you have to put in lots and lots of extra conditions that say that things are separate and don't alias. In separation logic, by contrast, there's a separating conjunction, P star Q, which holds of a heap when P holds of a disjoint part of the heap from that on which Q holds. So you can treat separation non-aliasing as the norm. And this dramatically simplifies reasoning about programs that do tricky pointer manipulations. So I think this really very much has revitalized the whole theory of program verification. I mean, there were lots of people working on programming languages and programming language semantics, but I really think it was separation logic that made a whole bunch of new people actually go and look at program logics and at proving programs correct. And it's had a huge influence on both theory and practice. So one of the ways that this is developed after the initial theoretical papers is a whole bunch of people have built tools for doing automatic program analysis based on separation logic. So there's a list of, I don't know, 20 of them, some of which are Smallfoot, jStar, Spacelnvader, Slayer, from people in my group. The state of the art here is these automatic tools are doing memory safety proofs for very large pieces of industrial C code. So they can take device drivers from Linux and Windows and verify that they have no memory leaks in them completely automatically by using separation logic, and then a lot of intelligence about how you actually do searching for proofs. Separation logic extends very, very naturally to concurrency. The basic thing you want to reason about concurrent programs is to know that two parts of the program access disjoint resources, and there's an extension where instead of just reasoning about the resources being consumed as being pieces of memory, you also reason about the permission to do particular things, and this gives a very powerful way of reasoning about even very tricky racy concurrent programs. So separation logic has been extended to higher order in a couple of ways, mostly by Lars Birkedal and his co-authors. So one direction of extension to higher order is to keep the store of flat pointer structures as it is in separation logic, but to allow higher order functions in the programming language. So this introduces higher order frame rules, which are quite tricky to get right. And the model that Lars and co. First used for verifying the correctness, the soundness of their rules for higher order functions was very much like the model that I was telling you about before. It's built on FM-cpos and uses relational parametricity and this top-top lifting construction. And then more recently, they've been looking at having higher order functions and higher order store, so being able to store state manipulating functions in the heap itself. And this is extremely challenging to reason about and model from a foundational point of view, because you've got recursion through the store, and pretty much everything that you ever do turns out to be recursively defined. So this involves nested triples. So this means that you can have an assertion about the heap, which includes an assertion that a particular location contains a piece of code which itself has a given pre- and post-condition in the logic. The model is a Kripke model. I'll say more about those in a bit. So it's parameterized by possible worlds. And the worlds themselves are defined recursively using ultrametric spaces, which I'll also talk about a bit later. So I've been talking about refining monads with effects and so forth, and there's been a very nice line of work, which I guess you may hear more about later, on refining state monads with dependent types. So Alex Ninevsky, Greg Morissette, Lars Birkedal, and a bunch of other people have been working on something called Hoare type theory. So Hoare type theory has a refined version of the state monad, which looks something like this. So P, x of type A, Q, is a judgment over your monadic type, and it classifies those computations which, when started in a state satisfying P, will return a value x such that Q is true of the post state. So this is something which has been embedded in Coq, and the ambient logic has full dependent types, and you can include separation logic assertions in these P's and Q's, and the embedding in Coq generates verification conditions and has some very powerful automation with it. So you can actually prove the correctness of programs which involve higher order functions and dependent types and state manipulation. And they've done a whole bunch of very cool examples of verified software, including very tricky imperative data structures, web services, and even a database management system. And I guess Greg's probably going to talk about that a bit later. So relational Hoare logic. So this is a very simple extension of Hoare logic to reason not about just one run of a program, but two runs of a program. So we can say that two programs have the property that if you start them in states that are related like this, then they will end up in states that are related like that. So this is something that I originally worked on, and in the context of proving the correctness of the kind of program transformations that you perform as a result of compiler analyses. And Hong-Sok Yang came up with much the same idea when he was trying to reason about refinement proofs for separation logic programs. So this can express all kinds of dependency analyses, including information flow and program slicing. And more recently, the idea has been extended quite substantially in the information flow direction. So firstly, there's a system called Certicrypt, which is by Santiago Zanella and Gilles Bart and others. And this is a probabilistic variant of this relational Hoare logic, which they've encoded in Coq, and they've used to verify some real digital signature schemes. This is serious computational cryptography verification, which they do basically by program transformation using the rules from this logic. You specify the computationally hard problem as a game, which they re-express as a program, and then show that they can perform a transformation of the program implementing your crypto protocol into the game in a way that keeps the information leakage under a polynomial bound. And Alex Nanevsky, Anindya Banerjee, and Deepak Garg have taken HTT and made it a relational version, so they now have a thing embedded in Coq which lets them verify information flow and access control policies for programs with all kinds of tricky properties, high order functions, and dynamically allocated references, and so on.